Let's look at an example that utilizes the exponential distribution. So we have an intersection here with traffic moving from, we'll say, left to right or right to left. And then we have a stop sign. So we can have a main road right here and then a stop sign that allows cars to stop and wait and pass. And so very kind of simplistic example here. And the rule we'll say here, kind of based on driver reaction time, is that we need a gap between cars of about 15 seconds, at least 15 seconds, for the car waiting at the stop sign to actually get up the muster and go. All right, given kind of the speeds of these cars and driver reaction time. So that's the setup here. The first thing we'll look at is finding the probability that a gap in oncoming traffic is at least 15 seconds on average if we have 10 cars pass per minute on average. So maybe that's data, those are data that we collected from rush hour, and so we want to figure out, do we need to put a traffic light in here or a traffic circle, and how long is a car basically going to be waiting. So let's take a look at this first example. And we'll use our exponential distribution. First, we're at the probability. So we'll say probability that our gap time, T gap, is greater than or equal to 15 seconds. All right. Now, greater than or equal, we see that and we're thinking, well, that's not a CDF, right? It's not a PDF. The CDF gives us less than or equal to. So let's rewrite that. And we can say this is equal to the complement, 1 minus the probability that our T gap is less than 15 seconds. And it's a continuous distribution, so the inequality sign isn't super important here. But all right, now we have 1 minus the CDF of the exponential distribution. And we can write this out again. So let's do 1 minus, and then we put in our CDF, which is 1 minus e to the negative nu t. And this again is the exponential CDF. And then now we can essentially plug and chug. So the parameters that we need to know, t is going to be equal to 15 seconds. And then nu is our rate parameter. That's going to be number of cars per time. And we note that we have to keep track of our units here. All the time units and rate units have to be in the same time base. And so just like flow can be in cubic feet per second or cubic meters per second or gallons per minute, we have to make sure we keep track of our units here. So in this case, we're going to do 10 cars per minute, which would be 60 seconds. And that is essentially, we'll just call it 1/6 number per second. All right, now we can plug everything in and we get 1 minus e to the negative nu t. Actually, we're supposed to plug that in, so let's do that. 1 minus e to the negative 1/6 times 15. And if we plug that in our calculator, we end up with e to the negative 2.5, which is equal to 0.082. So the probability that we have a gap in oncoming traffic of at least 15 seconds is about 8%. And this would basically be our probability of crossing. Now you could translate that back out into time or something like that by saying, okay, we have an hour and essentially 8% of the time people would be able to cross within that hour. Now let's take a look at another question we can ask in this example. And that is, what is the probability that it takes 4 gaps, so essentially 5 cars, or yeah, I guess it'd be 4 cars, and then after the 4th car, until the waiting car will cross. We can write this out by saying this is the probability that car crosses at the 4th gap. And we know that the gap has to be at least 15 seconds for it to cross. So essentially this is just saying we have for gap number 1, so we'll say gap 1, we have no cross, and then that's going to be an and. Gap 2, we have no cross, and gap 3, oh, let me just move that over. No cross, and then finally we get to gap 4, and we have a cross. And so essentially we're saying that t is less than 15 seconds, t is less than 15, t is less than 15, and then t is greater than or equal to 15. How do we write this out using the exponential distribution? Well, we just need to find the probability of all of these things. So p, and then we're going to multiply them together because Poisson processes are independent across intervals. And we'll note that we just calculated this from the previous example, and that this was e to the negative 2.5, which was equal to 0.082. And so this is simply the complement of that. So we can do 1 minus e to the negative 2.5, and we'll cube that, 1, 2, 3. And then we'll just multiply it by e to the negative 2.5. And then if we crunch that in our calculator, we'll end up with 0.063. So this is a probability that we'll have to wait 4 gaps until we get the ability to cross. Now, we're doing a couple of things here. Remember, we're doing the exponential distribution, but we're also using our probability theory. And so we know that between intervals, so we'll just kind of draw this out as an interval, T1, T2, T3. A Poisson process has a probability of happening anywhere within a time interval, and that between intervals, it's independent. So that's an important definition of the Poisson process. So because it's independent, we're saying calculate the probability that the time gap is less than 15 seconds per interval. We can multiply them together, 4 intervals, and then finally we get, or 3 intervals, and finally in the third interval we have something, we calculate the probability that's greater than 15 seconds. So I'll note that this is different from the binomial distribution. Kind of sounds a little bit similar, but the binomial will give us the probability that, for example, if we treated each gap as a trial and does the car cross or not, if we were to use that using the binomial distribution, it would give us a different probability because essentially there would be 4 different ways it could cross. It could cross during the first gap, second, third, or fourth. Therefore, we'd have essentially a higher probability there. But here we specified it a little bit differently. So it says, what is the probability that it would cross at the 4th gap? All right, the next thing we can look at is something a little more, I think, interesting and applied here is what is the average number of cars passing until the waiting car crosses? And this is something that would be input into a traffic model, for example. So we have the average rate that cars are passing, and we have cars trying to cross at a stop sign. So how many cars essentially would be stacking up over so many minutes or an hour waiting to cross here? So the way we would calculate this is we already calculated P of crossing, which is equal to the probability that our T gap is greater than or equal to 15 seconds, and that was 0.082. And all we need to do then is essentially the expected value of the gap time. And so that's just going to be 1 over P. So 1 over P is equal to 1 over 0.082. And so that gives us 1 over e to the negative 2.5, which gives us e to the 2.5. I'm just writing that out so we can kind of track that algebra there. And that's equal to 12.2. So because gaps are discrete events, we'll say it takes 13 gaps on average, before the first car can cross. So that is our brief introduction and an example of the exponential distribution.